So good afternoon, everyone. My name is Wes. Most of you probably know me since I've been in and around this community in the UK for quite a while. And some of you might even know me from the 1990s in the UK doing some LabVIEW stuff. So I have a good discount code on vitamins for the rest of you. So today we're going to talk about the um, LabVIEW sound and vibration toolkit, which is something that I have used before. We've used it over the years to do a balance test stand on a pair of gyroscopically stabilized binoculars, which were really cool. They were for astronomical purposes and they were amazing. They worked so beautifully well. When you'd move your head, the optics would stay perfectly still. And then we've also used this, I've used it to prove that certain of the components on the Mars exploration rover would survive pyrotechnic shock test events or ordnance excited shock events. And I'll talk about that stuff too. So this is a toolkit that I've actually used, and it's extremely powerful. And I'm just going to give you all a little bit of an introduction to it. So I've got some additional information later, but we'll start off with my slide presentation. So a little bit about us. You all know who we are. We're an NI Alliance partner. We are big in this community. Chris is a LabVIEW champion and one of the co-founders of GDevCon. So we are really passionate about LabVIEW and being a part of this community and helping others learn the tool and be successful with it. So part of that is to outreach with things that we've learned and deploying LabVIEW tools and systems, equipment, hardware, software in the real world. And today we're going to talk about this, which I'm in the middle of deploying right now for a couple of different customers. So we're going to start off with just talking about the toolkit. I will then walk through what it looks like to actually balance a piece of rotating machinery. You will see on the background, I actually have some live data, well, not live data, I have some data that we took off of a balance and rig, and then we can take a look at what that data looks like and why some of the things are important with relation to the sound and vibration toolkit. We can see how things might change over time if we have speed varying signals and things like that. So I'm going to talk for about 40 minutes. If anybody has any questions, or they're about 40 minutes, but shout up at any time. If anybody's got any questions, please just raise your hand in the chat or shout them right out, and Chris will either let me know that you're raising your hand or I'll answer your question directly. But yeah, happy for this to be a interactive demonstration, presentation, etc. All right. So why do we want to talk today about balancing rotating machinery? Well, for instance, I read a statistic the other day that a single cruise ship, so for instance, P&O cruises or any of these types of cruises, they have over 5,000 pieces of rotating equipment on a single one of those boats. And that's everything from those ships, they're not boats, sorry. Everything from the bow stabilizers to the main drive to elevators to pumps and fans, extraction fans, HVAC, etc. So rotating machinery is the basis of the modern industrial world. That cannot be overstated. And part of the things that we end up doing as engineers typically tends to be looking at rotating equipment, characterizing power consumption curves, torque, speed curves, at temperature, at all kinds of different operating conditions, loaded, not loaded, etc. So the sound and vibration toolkit comes in quite handy when we're looking at how to diagnose problems with rotating equipment. And there are many different types of problems that we can run into with rotating equipment. So we can have misalignment problems. So two pieces of rotating equipment mating together, and there can be axial misalignment, parallel misalignment, or angular misalignment. So we can have problems with unbalanced rotating equipment. So for instance, a flywheel might suffer damage and become non-isotropic or anisotropic, and can then cause rotation vibration on a piece of machinery that can couple into other machines, and it can cause catastrophic failures. One of the very important applications for rotating machinery is in uh, turbo machinery for steam turbines and gas turbines. These things are, you know, several tons of rotating equipment at operating at 3,000 or 3,600 RPM. And if they fail, if they throw out of the bearing, they can destroy entire buildings. So monitoring rotating equipment is an extraordinarily important part of mechanical engineering. And this is a very nice tool that National Instruments has prepared for us as engineers to use. And many of you may have seen it. It'd be interesting to see if anybody in the chat puts up the yes, we've ever dealt with rotating equipment. All right. So first of all, the sound and vibration toolkit. What is it? It is a secondary palette from National Instruments. Let me see if I can share this with you. So here we are. We can see that if we install the sound and vibration toolkit, which is a subset of the advanced signal analysis toolkit, it is a standalone product. We get a new palette down here called sound and vibration, and it includes everything from scaling and calibration to tone and distortion. So you'll see a lot of familiar things in here. FFT, fast Fourier transform, for instance, signal to noise ratio measurements, total harmonic distortion, things like that. Those are specific to sound measurements, but we also have a lot of things specific to vibration measurements. So in general, the sound and vibration toolkit is designed to use the so-called DSA, dynamic signal analysis modules within the NI hardware ecosystem, or any data acquisition hardware that's generally designed to do high fidelity data acquisition for sound and vibration. Now, mechanical vibration can be anything up to 100,000 hertz. Acoustics generally tends to be up to about 25,000 hertz because that's kind of the limit of human hearing. But we will see accelerometers and microphones working quite a bit above those things for different phenomenon. But for our purposes today, a balancing machinery, as we discussed, rotates at about 3,000 RPM for power generation. Three-phase motors operate at line speed, which is whatever the oscillating frequency of the line. So a rotating motor in most industrial applications will be operating at the synchronous speed of the grid. So in the United States, 60 hertz, and in the United Kingdom and Europe, 50 hertz. So we're looking at frequencies that are far below many other applications today, but you can imagine that this sound and vibration toolkit covers the whole gamut of these phenomenon. Basically up to the gigahertz if you can monitor those kinds of frequencies in displacement or vibration. But of course, those types of events tend to be extremely small amplitude, so they become unimportant in mechanical applications. Anyway, it includes your standard sort of fast Fourier transforms, everything that we would traditionally consider to be spectral analysis, or looking at the signals in the Fourier space or frequency domain. Order analysis, which is what we're going to talk today. So for rotating machinery, we might be interested in seeing what things are happening relative to a single rotation. And we'll see that balance is a phenomenon that is linked to the first order of rotation, which means that the primary challenge with machinery balance tends to occur at a frequency which is exactly equivalent to the rotating speed. And as the motor speeds up and speeds down, we will drive through transmissibility curves to achieve resonance for maybe the mounting structure, maybe the main shaft, maybe we'll hit the second mode of the shaft and all kinds of stuff. So it is important to be mindful of all of those things when we do rotating machinery balance and analysis. The toolkit also is, as we discussed, applicable to noise, vibration, harshness, so acoustic signals as well. And then you see on below, but we're not going to discuss any of that stuff today. We'll discuss a little bit of the spectral analysis and heavily the order analysis. So how does this work for you? Well, at some point you will have some, your customer will say to you, well, we need to, or your project will say, we need to monitor a piece of rotating equipment. And the sound and vibration toolkit sits somewhere between your application and the hardware. I believe that National Instruments intends this stuff to be very much black box, and we're going to look at that a little bit more closely, because if we look in underneath the hood of one of these things here, let's pull out a, we're going to open up the block diagram for one of these VIs, and you can see they're extraordinarily dense. They are not necessarily documented to be accessible. And I think that's intentional. So it is my opinion that this is really intended to be a black box tool for you, and not a learning experience or anything. In fact, if you go monkeying around with much of this, you probably would end up with an unusable analysis tool. So somewhere between your application and your hardware is going to sit the sound and vibration toolkit. Sorry, somebody's speaking. So is that a question?
No. Sorry.
Okay, so if you're maybe, yeah, let's mute. Yeah, everybody mute their mic unless you have a question, and then please feel free to join in. All right, so I'll continue. Generally, the type of hardware that you're going to be using is a high-speed analog digital converter. You're probably going to be using the DAC-MX stuff, or maybe NI-scope, or somebody else. You could be getting data from anywhere. This is completely agnostic to the data source. You do not have to use National Instruments hardware, but that could be running on compact Rio, compact DAC, etc. But in general, for rotating equipment, you're going to be using capacitance or Hall effect proximity probes, which will measure the position of the shaft relative to the bearings. Or you might be using accelerometers, and they might be IEPE accelerometers. That's a very common type for measuring bearing faults and things. Now, keep in mind that the proximity probes and the accelerometers are measuring two completely different things. Accelerometers are measuring the second derivative of position, and so there are some scaling and some phase considerations when you go from a proximity probe to an accelerometer, for instance. All right, for balance, if we want our machinery to be balanced for many good reasons. Number one, it could fail catastrophically if the misbalance of a machine exceeds the load limits of the bearings or any of these other things, and we could have catastrophic failure. So that's not very good. That catastrophic failure can be caused by gross overload on a rotating shaft. However, that's unlikely because you would detect that quite soon. But high cycle fatigue is a primary failure mode for rotating equipment. So you can imagine if we are getting near the yield strength of a piece of material, a structure, a shaft, and we're doing that, cycling it at 3,600 times per minute, it's going to experience high cycle fatigue sooner than later. So that can couple into the floor. So for instance, a brittle pad where a pump or turbo machinery is mounted, it could crack the concrete, cause water ingress or structural failure of other kind. It can be noisy and cause safety concerns for the operators or nearby people. It will cause energy. So if you're not balanced, your machine is using more energy than it ought to. And so that's, in the modern era, much more interesting than the noise. It can affect the ability to operate the tool. So for instance, in a CNC machine, if your machine is experiencing a high degree of vibration, you certainly cannot achieve your manufacturing tolerances. And then a very interesting one, which we learned about for spacecraft structures. If we have a machine that is operating, it's being excited by a harmonic excitation, so some periodic driving force, when it reaches its natural frequency, it actually can start taking energy out of the parent structure. And sometimes that's good, and you'll design systems to do that. But sometimes it's bad because then the input doesn't get to the amplitudes that you need, and you might be under testing something, or your system might be under actuating. So it's very important that that doesn't occur. So understanding the natural frequencies of rotating equipment and structures is very important. The sound and vibration toolkit is very helpful for that. Over here on the right, we've got a very, very coarse distillation of the ISO 1940 standard, which tells you that, for instance, if you are going to create a piece of equipment, they ought to be balanced to within some tolerance. So the displacement times the frequency in the third column for a precision instrument like a gyroscope or something ought to be 4 millimeters per second. So that's related to the frequency of rotation. A G1 class device like a gas turbine, which is critical safety device, should be very, very, very well balanced at 1 millimeter related to the speed. But then if you look away at the bottom, we got an agricultural or crushing machine. We can tolerate 16 millimeters of vibration. So depending on the machinery, you will certainly design your supporting structure to accommodate these different types of vibrations, et cetera. But you will certainly have to prove to somebody that your equipment is operating within the regulatory or requirements vibration levels. And so understanding what some of these levels are and quantifying them is always important. And so this is just a governing standard that you may see a lot of times. All right, so there are two types of imbalance on a piece of rotating equipment. The one we're going to worry about today is the static imbalance of a rotating equipment. So this is a sample. Let's imagine we have a flywheel, and the flywheel has taken some damage, so it is no longer uniform in shape, and therefore one side of it is heavier than the other side of it. So during operation, the rotating mass will produce a whirling action, and that whirling action will show up as vibration. And a static imbalance is one that occurs when we're running. It's off axis, so it's not on the center of the axis, which means that it can create some force. And it is generally it's running at 1 times the running speed. So if we're running at 100 RPMs, we should see a frequency of the vibration at 100 oscillations per minute. So RPM obviously is minute. If we divide that by 60, we'll get hertz. So that's how it's related. That's obvious. But keep in mind that a static imbalance will occur at the operating speed. So if we're running at 3600 RPM, we should see the frequency of the vibration at 60 hertz. If we're running at 3000 RPM, we should see the frequency of vibration at 50 hertz. Okay, so we're not going to talk today about a dynamic imbalance where maybe we have a couple of different flywheels on a shaft and 2 different bearings. In fact, anytime you constrain a rotating piece of equipment with 2 bearings, if there is more than one plane, or that plane isn't shallow, so if our flywheel now has some axial depth to it, it becomes a dynamic imbalance situation. So if we have one pump mated to a gearbox, or if we have a gearbox mated to a propeller, for instance, I'm making these things up, anytime we do those couplings, we have created, by definition, dynamic imbalances. And these things always interact, and they have often different frequencies, different phase relationships between the devices, because each of the devices will have their own natural frequency in the structure, etc. So we're not going to discuss that today, but the mathematics are shown. We won't discuss it. So order analysis is important for us because the imbalance on rotating equipment, static imbalance, always appears at exactly 1 time the running speed. We will find potentially other sources of problems on rotating equipment that doesn't occur at 1 time the running speed. For instance, if we're looking at ball bearings or roller bearings or needle bearings, we can detect damage in roller bearing elements by looking at higher non-integer frequencies of the operating running speed. So there are other things to look at, but for purely balances, we're only worried about looking at the 1 times running speed. So that's called the 1x order, the first order. So order analysis nomenclature, 1x. And we're going to be worried about the magnitude of the imbalance force. How far is this thing moving from its center line position? And what is the phase relative to some reference? So we always have to have a reference. We'll talk about that. So we'll set up the measurement. For the most part, the most common type of measurement is an IEPE or ICP, integrated electronic piezoelectronic accelerometer. And these are available very easily from PCB or a number of other places. And generally, they come with little magnetic housing, and you just walk into a factory, you place these things on the bearing housing, and you take your measurements. Interestingly, what they are measuring is the response of the mounting structure and not the shaft. So if we go to a more in-place balancing application, we might be using proximity sensors, and the proximity sensors will measure the actual displacement of the shaft center line relative to some datum position. So this is a more useful diagnostic, but it requires a permanent installation because the air gap between the sensor and the shaft must be characterized at the time of the setup. Most in-place permanent rotating machinery diagnostic equipment uses proximity sensors. Most portable balancing kits will use accelerometers. Now, the SVT can handle either of those. But what we must have in addition to the accelerometers or the proximity sensors is a tachometer or a key phaser. Quite often, shafts are coupled using keyways. So it's a little piece of metal that you use with a coupling, and it inserts and forms a little shear element between the coupling and the shaft. And they are designed for that very purpose, because if there's an over torque event, the little key will fail, not the machinery. But because the key is once per revolution, they are very often used as our once per revolution reference. And so you'll see that term called the key phaser. Anytime there's a key and we can have access to it with our little proximity sensor or whatever we're measuring, our tachometer, generally that's what's used. So you'll often see the term key phaser. Tachometer is a more generic term where maybe it's an optical system and we have a retroreflective target and we're seeing that target go around the shaft, and we can then reference all of our measurements to that datum position on the shaft. So everything is required. For rotating machinery balance, we must have a reference signal tachometer once per revolution. You can do an encoder, for instance, that's 30 or 128 lines per revolution, but that's not necessary. So the bottom line for us is the phase reference is 0 when we are right over that target, whether it's the key or the retroreflective target. And our data acquisition must be synchronized with this signal. Now I'll show you what that means. We're going to go over and take a look now at some data. So we can see this is some real data that I acquired just last week. I'm going to zoom in on the very beginning of this data. So we can see that at the start, my shaft is running at a fixed speed. If I go in time, we should see that these things start coming closer together. So that means that the shaft is accelerating. I'm sorry, guys, I don't know how to do this a little bit more conveniently with Diadem. What I want to show you is that eventually I'll get to the point where my signals are coming closer together, because now I'm speeding up. And when I speed up, you can see I still have the same number of mechanical events between the tachometer pulses. So the black is the tachometer pulse, and the purple and the yellow are my two proximity sensors. So in every revolution, I'm seeing two events. Now, if I go to a place where I'm going to zoom in right in the middle, where we're going much faster now, you can see that I still have the two per event, still 2 times per event. So it doesn't matter if we're running 10 hertz or 100 hertz. I know that per revolution, I'm still getting the same number of points, these little tiny peaks here. So that's what we mean by order analysis. If the speed changes, I'm still measuring things relative to one revolution at a time, no matter how fast we're running in speed. So that's just the key takeaway from that for what that means. So now the first thing we do is we look at the raw signal. Here's the raw signal. And we say, okay, we've got our key phaser. That's nice and robust. I like that signal. Let's zoom out and we can find a place where I'm going even faster. Oops, that's not what I wanted. We should see these things start coming. Okay, so now you can see, look at this. My purple signal starts changing a little bit. Do you see it? Maybe you can see it growing in amplitude and shrinking in amplitude. At some point, we're going to get to where we're at a resonance point, and the system is going to respond more than before. And here you can see that. So the purple signal has some sort of an envelope around it. It's growing, and then it's shrinking again. So now we look at the raw signal and say, what is happening mechanically here? The shaft position is changing as a function of time, even though it's not changing from revolution to revolution. All right, so the signal looks pretty good. Then the next thing is, do I see any impacts, sharp spikes, or anything else on my signal? Because that would indicate a mechanical interference or a bearing breaking or something like that. So it's looking pretty good. There's no clipping, which means my sensors are okay. My data acquisition is set up okay. I can see this signal very nicely. I can see the oscillatory component of my signal quite nicely. And so I would conclude, okay, this is pretty good data. I'm gonna be able to work with this. All right. So now the tachometer pulse in the same time base shows you one revolution. Between this pulse and this pulse is always one revolution. Everything will always be referenced to that revolution. So first thing we do is we just take a reading with LabVIEW, and then we use the SVT scale voltage to engineering units. Now, there's a whole workflow that you have to go through in order to get to where we're going. And I'll put this up here. So we've got, this is the fake signal data from a shipping example. The shipping examples are very good, so you can go and play with these even for fun. And although the sound and vibration toolkit costs money, you can get a 90-day free evaluation, and it's very fun to play with. I mean, if you're a nerd like me. All right, so let's take a look at the simulated data. So I can run this. We got some simulated data coming in. We've got some power spectrum. So this is your traditional FFT. So that is done with one of the tools, the order power spectrum. But everything now is relative to one revolution at a time, no matter what the speed is. So we can see our speed is going up in time. It reaches some peak and then it ramps down. But during that time, we'll be able to calculate the principal frequencies as we go. So you can see we've got some startup stuff at low frequency. Maybe there's, and then this is the primary operating mode right here. So that's your first order. And then we can look at some other things. But the processing of it requires you to extract the tachometer signal. And then you can do all of the other things you need to do, maybe RMS, maybe FFTs. And we can look at some of these other examples later, depending on time. But the toolkit is very sophisticated. And then we can look at, we can integrate the signal. We can do RMS levels, so root mean square. So if I need to convert from one standard to another standard, I can find the peak values, which is very important for us. And then we might want to look at the frequency domain. So every engineer uses FFT for almost all data acquisition analysis. The first thing we do after we look at the raw time signal, it seems, is we're always looking for an FFT. And that makes sense because every structure we deal with tends to be a classical single degree of freedom mechanical oscillator. And we're going to talk about that a little bit later. I've got, so we're going to talk about what is a classical mechanical oscillator. But the point is, so an FFT is completely appropriate when we're looking at a rotating piece of equipment. Geez, I've got lost. But we will see at times that it isn't sufficient to tell us exactly what's going on. And furthermore, the FFT requires us to be at a constant speed. So do all the things that you do with your standard frequency transforms, and we will get a nice clean signal from the tool that says, okay, I can see what's happening in my rotating equipment. There's something going on here at 1 hertz. There's something going on at 2 hertz. There's something going on at 3 hertz. So that indicates to me that we've got some sort of harmonic going on. It's probably a startup transient. And then we've got our main operating frequency, which is at 10 hertz. So we're running at 6,000 RPM. 10 hertz is once every 6 seconds, or 6 times per 6 times every 6 seconds, so corresponding to 6,000 RPM, which is a weird measurement, but that's what the demo gives us. We can also run from a different thing, but we'll always capture the primary running frequency. The order analysis toolkit allows us to see that that is the primary frequency, even if we ramp up and down. All right. So some of this is a little bit obscure, but it's interesting because this is what we need to do when we look at rotating machinery. And the nice thing is that the LabVIEW tool lets you do all the sophisticated stuff kind of with the black box. But if you don't know what the black box is doing, then you can't get meaningful results for your customers. So the limitations of finite Fourier transform, or fast Fourier transform, or discrete Fourier transform, is that if the speed varies, our peak will move. So for steady state machine, if it's running at a constant velocity, that's fine. If the speed is varying, you need order analysis. So order analysis says we're going to acquire the vibration or the proximity and the tachometer signal simultaneously. We're going to then plot everything relative to 1 revolution at a time. So the order analysis digital tacho process, order analysis convert to even angle signal, all of these tools are available to you in the toolkit. So here's the OAT analog tacho process, and we have a number of these that we can see on the palette. We don't have time, obviously, to go through all of this stuff here, but you can see that those tools are provided for you, which is quite convenient. Okay, then we say the amplitude of that signal while we're rotating it tells us how much unbalance there is. And the phase angle tells us where on the shaft the damage might be. So let's say, for instance, if the flywheel has the face of a clock on it, 12 being the top dead center. And let's say that the mechanical damage occurs at the 3 o'clock position. By measuring the phase angle between the tachometer pulse and the maximum displacement at the critical frequency, we can find now where on the rotating equipment the damage occurs. So using this toolkit, we can say, well, we have an approximate imbalance of X number of grams at this radial position and at this circumferential position. So what we have to do to balance it is we have to add a trial mass and then take another trial run with the trial weight installed, and then we compute what's called the influence coefficient. We're not going to go into the math today. It's a little bit complex, but the point of it is when you go into a factory, you measure the imbalance, you put a trial weight in place, and sometimes it's even just an adhesive piece of lead that works quite well, actually. You run the thing again, you compute this influence coefficient, and the algorithms tell you, okay, your imbalance is at 14 degrees counterclockwise from your tachometer location or your key phaser, and then you can add a correction weight, and you've balanced your machine. So out of the box, we can see this is real data on a older balancing device. So as the system runs up from 286 RPM, 700 RPM, 1000 RPM, 1263 RPM, you can see the behavior of this machine changes until we hit the maximum displacement at 1400 RPM. And the maximum displacement is way off the chart. So this device is terribly unbalanced. But now you can see also we have this 0, 270, 180, and 90. This is a standard what's called polar plot. As we run up through speed, the system is recording the imbalance. And at some point we see a maximum imbalance. And that generally corresponds to the critical frequency, which is the operating speed. Then when we go higher, the system is no longer responding as a 1x, and the amplitude actually gets lower. But at our operating speed, we have a maximum amplitude of imbalance. After balancing, you can see that with the application of the balance weight, the phase angle is completely different because we've added a balance at the correct location, and the amplitude is much smaller. So that's what a balance plot looks like before and after. And this was from a Bentley, Nevada balance tool. This is the old school standard for balance in the industry. If you're ever out there doing balance equipment, you're going to run into Bentley, Nevada. And then they became Baker Hughes, and that was bought by General Electric. So now all of this equipment is General Electric. This plot you can see is definitely from the 1990s, but that's the data we have because we're replacing this machine. If you have two system, a two-plane system where we talked about earlier, that dynamic imbalance, you have to solve a matrix equation, which is still trivial because we have modern tools to do that. So it's not a problem. You just calculate where in each plane the imbalances, and then you have to actually calculate how they relate to each other. How do they couple into each other? And that can be then corrected, and so you can balance a piece of rotating equipment. All of that stuff is built right into the SVT. So if we look at the, let's search for order. Oh, geez. Let's search for the influence coefficient should be, or coefficient in the SVT. Let's look for balance. Anyway, all of their stuff is available. Why won't it? Now my LabVIEW is not searching. Sound and vibration toolkit. It's not searching for everything I need. Of course, during a demo, it won't. But the good thing is there's so much stuff available in here that you will never run out of capability. And again, it's fun to play with. So if you're interested at all, you can download it for free. Orbit plot. So let's say we have two proximity sensors on the shaft. We can do some additional diagnostic on a shaft. So this is the actual physical displacement. You would expect it to be round if it's uniform, if the mounting structure is isotropic. What this is telling you is that my bearing pillow block isn't as stiff in the left and right as it is in the up and down, or something like that, depending on the relationship between the key phaser and the proximity probes, or wherever you're measuring them. But you can do some diagnostic on that. Now, what do engineers do when we don't have something that works well with the Fourier transform? We don't have something that is 2 pi periodic, because remember from your mathematics, when you learned about Fourier transform, we learned that everything that we can represent with a Fourier transform means that it's an infinite summation of sinusoids, and sinusoids are 2 pi periodic. So what do we do when we have harmonic excitation or non-harmonic response? So now we come in with what's called the shock response spectrum. And I know an awful lot more about this because I've used it to do characterization of spaceflight hardware for survivability, because spaceflight hardware does there's a lot of explosive stuffs on rockets, right? You've got rocket initiation, through bulkhead initiation, stage separation, you've got fairing separation, gas bag generation, all kinds of these things. They're all powered by explosives. And an explosive event isn't 2 pi periodic. So we have to find a way to analyze these signals, and the inclusion of the shock response spectrum in the LabVIEW sound and vibration toolkit is actually extraordinary, because this is a very, very esoteric algorithm. But when we're looking at a shock event, shock events in the time domain look like this. They're characterized by a high peak, very fast rise time, and then some kind of a decay curve. And you can see down here, some structures responding at a 2 pi periodic way, but the shock event itself is not periodic. So how do we know how our structure responds to that if this is the excitation? We can't model that in the Fourier space. We don't have any way to model this in the spectral domain. So the algorithm looks like a bunch of tuned single degree of freedom classical oscillators mounted on a board. Each of them has different K and C, so they have a different natural frequency. And then we hit that board with a shock, and we see how far they all displace. This is the so-called maxi-max algorithm. So if this mass number 2 displaces this far at that shock, we just reproduce the curves, and we can learn a lot about the system response by looking at this curve. So here's our peak shock loading. So a device that had this natural frequency, omega 3, would see the worst displacement based on the shock that we hit it with. This is actually how the algorithm works. In the old days, they literally had these frames of the little devices, and they would hit it with the shock. That's how they did it for the Apollo program, which is very interesting. They still have a couple of these things lying around at the Jet Propulsion Laboratory, and they're magnificently beautiful instruments. Okay, so what else can we learn from balance, from order analysis, and all of the information we'll get out of the sound and vibration toolkit? So we can detect misalignment. We can detect misalignment, bearing faults, so rotating bearing elements, broken balls, cracked bearing races, all that kind of stuff. We can detect damaged gears, or when a gearbox is not meshing correctly with a drive, because if the drive is trying to run at a speed that the gearbox doesn't like, you'll get some characteristic frequencies. So that's higher order FFT. Oil world tells you when your shaft is moving in your, you're getting some delamination or cavitation in your oil. Resonance frequency is obvious, and then looseness for things just not fitting well together. So the sound and vibration toolkit can help you with all of these things. If a company's got any rotating equipment, you can do a heck of a lot of diagnostics with the SVT. And then, so your next steps, I suggest go and download it. It's extremely powerful. It's installable now up to LabVIEW 2026. You can download it and play with it for free. There's a ton of examples, both for acoustics and for vibration. And yeah, I just recommend it. So at this point, I will stop. There's really nothing else to say. The Sound and Vibration Toolkit is a serious measurement laboratory that encompasses an awful lot of mathematics. Like, we can't go into the mathematics. It's a whole semester worth of graduate level mathematics that we do not want to cover today. But the key point of all of this is that if you're going to look at rotating equipment, you must do it with order analysis, because then you can relate everything to the rotating speed of the equipment. The speed of the operation is irrelevant to the diagnostic that you can do. The phase relationship between things in structures and in rotating equipment is just as important as amplitude, because if you if you don't know where your imbalance is, you cannot fix it. So we look at the relationship between the shaft position and the key phaser to know where an imbalance is at operation. So never forget to record phase. Then the so-called influence coefficients that help you correct for the imbalance is the methodology that you use to apply a balance weight. And we can do a lot more diagnostic than this with the sound and vibration toolkit. We can even look at the toolkit a little bit, and there are good examples and things like that. So I guess for now, I'll open up the floor to questions. And it was pretty nerdy talk, but pretty important. And this is real shipping code from National Instruments that's very, very powerful.
Awesome, thanks, Wes. Appreciate you putting the effort into putting that together. And yeah, I guess open up for any questions. Obviously, people might think of them after the event, but Wes is always open for any conversation that might go on afterwards. So
I'll put my email in the for anybody who wants to get a hold of me. My email is in the chat, and please feel free to contact us if you just want to talk about balancing or what's the difference between an accelerometer. One of the things I didn't mention was if you're using an accelerometer, which is a heck of a lot more common than using a proximity sensor, there are a lot of things you need to think about. The phase relationship of the shaft is that it scales with omega squared, so the operating speed squared, and you are capturing the motion of the housing, not the shaft. So you have to think about what resonant frequencies are you measuring, etc.
There's a question from Charlie. He's got his hand up.
Hey, go ahead, Charlie.
Hi, thanks, Wes. That was a really good presentation. I just got a few questions about it. So I do quite a lot of work with rotation as well. And I was just wondering, when you talk about using the toolkit on rotation, does it tend to be on open loop systems or closed loop systems that you're doing the analysis on?
We're absolutely. Oh, so you're saying like a servo versus a non-servo?
Well, I was just wondering, like you were talking about like measuring the imbalance and then adding weights to it to try and rebalance it. Do you, on a closed loop system, do you find that masks some of?
Yeah, absolutely. In fact, this is very interesting. If we run the FFT, for instance, on the data that I was showing you on Diadem, we will see a little contribution very near to the central peak. And what happens is, if you're running in closed loop control, the servo loop is continuously changing the velocity to make sure that, it's continuously changing very tiny, minute little values. What happens is, if you have a flexible coupling in your drive line, that flexible coupling adds a little bit of resonance for that now torsional excitation. So when you adjust the velocity of the rotating equipment minutely with your control loop, you're introducing torsional perturbations. Those torsional perturbations are absolutely visible to the toolkit, and furthermore can cause resonance with a bellows coupling particularly, or helical or bellows couplings particularly suffer from that. So you'll see a tiny little peak. But now here's what's interesting. You have to be running at such a speed and data acquisition rate so that the bin of your FFT is suitable to see that tiny little peak. But I would expect to see some off principle frequency dither in a servo controlled system. Absolutely, Charlie.
So what would you do? Would you run it open loop or detune it? And then
you want to run it into a load at steady state with minimal gain.
Okay.
Like if you can apply some sort of, drag to it, so you're adding damping to the system, right? And then you have to lower the gain of your control loop if you can, so that it's operating in dumb, essentially as far as you can to open loop. However, that tiny little servo correction won't affect the principal balance calculations in reality.
Right.
But it's very interesting, but probably fifth order effect.
Okay.
I told you this was nerdy.
No, it's really interesting. Thank you.
It is a very cool problem. And analyzing. Let me go back to this. This is where engineers live, right? So everything we learn about the world is a second order system. In fact, what we were just talking about a moment ago, your control loop is almost certainly a PID, proportional integral derivative. And those PID, that PID concept is 100% directly relatable to this mechanical analog. Spring, that's your proportional. Damping, C, that's your velocity. And mass, that's your second order term. So anything related to the acceleration, an LRC low pass filter is a second order system. Your PID is a second order system. Most mechanical structures are second order systems. So our first tool as mechanical engineers is to go to an FFT. So yeah, it's interesting. You will definitely see that everywhere.
Yeah.
There
So
is a,
if I wanted to use this on a system to kind of to balance at the start, then sort of do it before I do any sort of detailed PID tuning, and then do that afterwards.
Yeah, I mean, so this for the rotating equipment we're talking about. If you're in a mode where you're controlling something, you're almost certainly ramping up and down in speed as a part of your mission statement, right? And as you ramp up and down in speed, you're going to be driving through the resonant frequencies of everything you're attached to. So maybe at 30 hertz, you're exciting the mounting structure. Maybe at 330 hertz, you're exciting your payload. And so it's a little bit less interesting to do balancing on a servo controlled rotating equipment than it is on a constant speed rotating equipment, because where are you balancing? Are you balancing it to protect your payload? Are you balancing it to protect your structure? So there's some other questions you need to ask yourself.
Right. Okay.
Any other?
there's one in the chat, Wes.
Yep. How are imbalance and vibration managed in rotating components like reaction wheels or turbo pumps to ensure system stability? So I would say to you that a turbo pump would be a very high speed system. A reaction wheel, maybe not such a high speed system, unless you're doing it like for gyroscopic stabilization or something like that. So in a reaction wheel, I wouldn't worry about it so much. In a turbo pump, I would worry about it a lot, especially if it's running at high speed. The interesting thing about when you're pumping fluid, actually, if Mark is on the line, he probably can speak to this a little bit better. Because now, what are the implications of doing rotating balance on a pump, for instance? Mark, if you feel like jumping in on that, otherwise I'll keep going.
Yeah, sure, I can jump in on that. So typically on pumps, the impellers themselves, so the parts that go on the shaft, are actually designed with excess material. So you can then actually on the balancing machine away deliberately some of that material to achieve a balance. So on a complex shaft with several parts, the parts themselves are balanced, and then the shaft assembly is then also balanced separately. But typically on large components, as I say, they have material deliberately added. So you've got scope then to remove that during manufacture.
So you're going to balance the entire assembly. So it's interesting when you're moving
parts individually and assembly.
Assembly. All right, excellent. Thank you, Mark. And Mark has experience in turbo machinery, which is why I asked him to just weigh in on that in a production setting. So he's actually our resident expert in that. Thank you very much. The interesting thing about when you're pumping something, when you're pumping a fluid, whether it's air or oil or any other kind of thing, the nature of the non-steady flow through the pump changes almost continually the dynamic response of the system. The damping changes, the viscosity changes in the material, the amount of fluid in the pump. It's not unless you're running at steady state, this balancing question becomes a little bit less relevant. Because if you're moving up and down through speeds, you might be moving up and down through transmissibility curves, and then it's a different challenge entirely. I don't know if that answers your question, Bhakti, but if you could indicate with a thumbs up or a thumbs down. And then Yuri, the most advanced tool I worked with was tip timing software based on LabVIEW, SVT, and oscilloscope. Nice. It's that's an extraordinarily interesting thing, because in addition to watching the blades as they go by, if your data acquisition system is sophisticated enough, you can actually see the motion. So you've got the macroscopic motion of the tips going by on the rotor, and then you can detect the actual in-place vibration of the blade itself. And that's an entirely other thing. So the blade itself will have a resonant frequency, and then the rotor will have a rotational resonant frequency. So that is an extremely interesting application.
Okay, we'll probably have to draw a line there and take a quick 5-minute break before the next one.